All right, and so what we're looking at today is the derivatives. Well, this whole unit, in fact, is called the derivatives of special functions or unique functions. And the first one we're going to look at is the derivative of a specific exponential function, which is y equals e to the power of x. Now, exponential functions model rapid change like population growth, compound interest, earthquake intensity, radioactive decay. Something that I know I've touched on all of those when we're dealing in advanced functions. Now, this number e is actually a number. It's 2.718. Now it keeps going on and on and on. And it's named after mathematician Leonhard Euler. Now it's spelled with an E, but it's because he's Swiss. But his last name's Euler. But that's where the E comes from. It's just his last name. Now, why do we care about this function? Well, given the graph of f of x is equal to e to the power of x, and I want to sketch the derivative, well, the derivative, as you can see early on in e to the power of x, when we're less than, when the x value is less than 0, the slope is very small. And again, your derivative is the slope of your tangent line at certain points. And so the slope of your tangent line is very small. But then the slope starts to increase as we get towards x equals 0. All right, and then what happens after x equals 0? The slope of the tangent increases dramatically. Now, again, why we're going through this function is that the graph of f of x is equal to e of x is a special function because the derivative of f of x is f prime of x. The derivative of the function is the function. So in that case, what that means is, well, therefore, if y is equal to e to the power of x, actually, you know what, I'm going to draw that in pen. It's always nicer. So if y is equal to e to the power of x, well then y prime is equal to e to the x. It's got to be it's the easiest derivative to find, I think. All right, now we could also have a function in for our, because again, e is a number, but we could also have a function as our exponent. And so if that happens, we just using the chain rule, we write down our original function and then take the derivative of our exponent. All right, now we're going to try some derivatives of our exponential function here. And so, for instance, for number 1, it says find the derivative of f of x for f of x equals 4e to the power of x. And in this case, finding the derivative, there is no function in the exponent other than just a plain x. But we have a 4. That doesn't change. That's just a constant out front. And then I take the derivative of e to the power of x, which is just e to the power of x. So again, just because there's a constant in front, the derivative of the function is the function. All right, now a little bit different scenario here in example 2, where it says find the derivative of f of x. Now we have a function that's not just a plain old x in for our exponent. So again, I want to find the derivative. And so we have our original function first, e to the power of 3x. And then you take the derivative of the exponent, which is just going to be a 3. And so really our function would be 3e to the power of 3x. All right, so let's get a little more complicated here. Nothing too crazy though, after a long weekend. We have our next derivative. So we're going to find, we've got f of x is equal to e to the power of 4x minus 1. All right, so again, I want to find my derivative. First off, we have the original function, e to the power of 4x minus 1. But then you have to multiply, again, using the chain rule, the derivative of the exponent itself. And this time it's just a 4. And so our final derivative would be 4 times e to the power of 4x minus 1. There we go. All right, example 4. Again, nothing, just a little bit different. We got a little more of an elaborate function as for our exponent. But again, when I find the derivative, all right, so we've got f prime of x is equal to, again, we just have our original function. I'm going to write it down first. That doesn't change. So e to the power of x squared minus 5x. And then, of course, using the chain rule, we have to take the derivative of the function in the exponent. And so we have a 2x. And then the derivative of negative 5x is minus 5. So I could leave that like that or write it as f prime of x is equal to, put the 2x minus 5 out front. It's probably nicer looking. Times e, again, to the power of x squared minus 5x. And there we go. All right, let's again just take another step up here. Again, nothing too crazy. Determine, this is something we've done before, but not with this function. Determine the equation of the tangent line to the curve y equals x squared times e to the power of x at x equals 2. All right, well, if we want to find the equation of the tangent line, first of all, at x equals 2, we need to find the derivative. But in this case, we have two functions. We have an x squared and an e to the power of x multiplying each other. So I'm going to have to use the product rule, which again is take the derivative of the first function, which again is going to be 2x, times the second function, which is e to the power of x, plus the first function, which is x squared, again, times the derivative of the second function, which, well, the derivative of e to the x is e to the x. Now, slope of the tangent line. To find the slope of the tangent line at x equals 2, what we're looking for is find the value of our derivative. And we draw that big line there to show that we're going to sub in a value of x equals 2. And let's see, what would we end up with here? We have a 2 already, times x, which is 2, times e squared, plus, let's see here, 2 squared is 4, and then e squared again. Now I can combine those because really I got 4e squared plus 4e squared, so in total I'm going to have 8e squared. All right, so now we want to find the equation of our tangent line. And so right now, if I'm looking for what we have so far, again, our equation of our tangent line is going to be in the form y equals mx plus b. And so right now we have y equals our m, our slope of our tangent line. I'm just going to leave that number. I'm not going to figure out e squared. Just leave it as that. So our slope is 8e squared times x plus b, where b again is our y-intercept. All right, so I'm going to sub in a point at x equals 2 to find our b value, but I actually need to know when x equals 2 what our y value is to be able to sub in a point. So let's see here. Let's try a different color. So if x equals 2, y, I'm going to substitute into our original function, which is, let's see here, we got x squared, so again, I'm going to have 4 times e squared. So I'm going to sub that point in to find my b value, and then I've got the equation of my tangent line. So let's see here. So I'm going to sub in point, the x value was 2, The y value is 4e squared into the equation to find our y-intercept, which again is called the b value. Never understood why, but it is. All right, so now what we have, let's see here, subbing into our equation, y is 4e squared is equal to, let's see, we have a slope of 8e squared times 2, because that's our x value, and plus b. All right, let's see, I guess I could simplify here. So we got, again, 4e squared. If I have this 2 times the 8, I've got 16e squared plus b. All right, I'm going to now get b by itself, so I'm going to move this 16e squared over to the other side, so it becomes a minus 16e squared. And so I would have 4e squared minus 16e squared. Well, that would be minus 12e squared. Again, that's actually a number I could figure out, but not going to bother. I'm just going to leave it as e. Oops, minus 12e squared is my b value. And so finally, I've got my equation of my tangent line. So because I have my slope and I have my b value, so the equation of the tangent line at x equals 2 is, we got y equals, the slope was 8e squared times x, and then plus our b value, which in fact we're going to go minus 12e squared. And there we go. So again, our exponential function, this is a special one, again, because the derivative of e to the power of x is e to the power of x. Probably the easiest derivative that we are going to be able to find.